right, let's move on to part 3 of module 5. We're going to continue on with money management. And what we're going to do is we're going to take that equation we had for when we actually had compounding periods that were different from the payment period, or maybe actually the same as the payment period, but the annual and the effective had, we weren't compounding annually, we were compounding on a different period. So we can take that equation that we had and make it a little bit more generic. The I equal 1 plus R over CK to the C minus 1, where C is the number of interest periods per payment period. K is the number of payment periods per year. So M is equal to CK. That was the M from before. And that was the total number of interest periods per year. So R plus over M was the nominal interest. Okay, so we got all those pieces together now. But now we can just use this equation to figure out the effective interest rate. Okay, which is kind of important. That's how we actually do this. So let's say we might have a payment period that's quarterly and a compound period that's monthly. That's relatively common. So you now have to calculate an effective interest rate. And what we really wanted to calculate is the effective annual interest rate. We can get the effective interest rate per quarter. That one's relatively straightforward, but we can get the effective annual interest rate by just applying the equation. I'm going to leave this up for a second so that you can take a look at the numbers and be able to substitute them into the equation correctly. Now, let's look at another one. Continuous compounding. Right, well, it's got the same equation that we've got right here. We're going to put this together, but now what we need to do is think of the concept of if you're continuously compounding, and of course, you don't actually compound all the time. It's a mathematical trick. So what does it allow you to do? It allows you to knock up that real interest rate that you're paying. So essentially what we're doing is we're saying we're going to take C and just make it approach infinity. And when you do, the final you get is e to the r up to the 1 over k minus 1. Again, it's just an equation. Okay, it's just an equation. It gives you an effective annual interest rate. So you can now look at what it's going to come out when you do the compounded quarterly. Ba-da-doom. You can look at compounded monthly. Okay, notice that number went up. Okay, you can compound weekly. Notice the number went up. And you can compound continuously. And notice the effective annual interest rate went up. Let's compare all those. Quarterly, 2. Monthly, 2.013. Weekly, 2.0186. Compounded continuously, 2.0201. And you say, oh, that's not a whole lot of difference, but it adds up. Okay, continuous compounding. When you're going to see this? When you need to make payments, of course, because it's just a way of saying, okay, we're going to really make that interest rate go up by just a little bit. You should look for it, but now you know how to calculate it. And again, it's just an equation. It's a relatively straightforward equation to do. So how do we do this? How do we actually do all these types of calculations? Well, the first thing is just it's equivalency analysis. You identify the payment period, identify the interest period, and then you identify the effective interest rate over the payment period. And you've got the equations. You just apply them into the equations. Now, sometimes the payment periods and the compounding periods coincide. This actually makes it relatively simple. Okay, you can do the, and this is done. I'm going to give you a nice little example here. Okay, calculating auto loan payments. A little bit more complex. You've got a few pieces of information here. You've got a sales tax, dealer's fee, purchase price, down payment. You've got a dealer's interest rate and a length of financing. And what you want to do is you want to calculate that monthly payment. So essentially what you're going to do is you're going to take the amount of money, okay, present value 20,000, 8.5, 12 payments per year, 48 payment periods, okay. This is pretty simple. You can calculate the this value by simply putting it in, okay. You're substituting into the equation. You know what that interest rate is on a per monthly basis, 48 months. You apply it in and you get an annual payment of $492.97. Okay, well, straightforward. Okay, now let's go to, what if we want to pay off the loan before everything is due? So somewhere along the line of the 48 payments, you say, you know what, I'm making these payments. So how do you calculate that? Well, in this case, you can know what the value of the payments made is at a specific point in time, and then using that value, calculate the number of payments that you have to complete the payment of that amount. So in other words, you have some payments that were made, and you've got the payments that you have that you would need to complete this. And you put this in you put this in terms of the value at that specific point in time at 25 months. All right. Okay. If you got questions with that, that's a good one to bring to the board. But again, it's just an application of what is the value of where you are at a specific point in time. And in other words, you did pretty good paying it off at that specific point in time. But notice that you did more time, 25 months, than you actually have outstanding 23, but you still have over half the original amount to pay. General rule, remember, the money that you paid early in the loan paid off less of the principal than the money that you're going to make later in the loan. All right, well, we can actually use this to do all sorts of types of calculations. For example, suppose you bought a pack of cigarettes every day for 50 years. Okay, in this case, we're going to say $1.75 a pack. They don't cost that anymore, but hey, that's just what we're dealing with. $19.97. We may take this one forward and actually change the prices. So, okay, if you banked that, how much money would you have had over those whole 50 years? Pretty amazing to say that if you smoke 3 packs a day, okay, annual interest rate of 5.5, we assumed that, and wow, $507,976. You would have had $500,000 just in that. How does that calculate out? Okay, effective interest rate per payment period, equivalence value, apply the equivalence value, and just simply do the multiplication. Again, I am not going to go through the details in the video. You have the numbers. Write it down, work it out, okay? Make sure it makes sense to you. Yeah, I know there's people that don't smoke. Guess what? I'm going to get you on it too. Let's drink a cup of Starbucks coffee, which does not cost $2 a cup. I think there's some places at your Wawa, you might be able to get it at $2 a cup, okay? Okay, what if we just put that money in the bank? Okay, what would happen? Well, let's find out what would happen if we put that money in the bank. Okay, again, you know the process. You figure out that effective interest rate. In this case, it's interest rate. In this case, it's on a daily basis. 30 years, 10,950 days, $50,000, $50,831. So you spent some money on some coffee there. Now, the payment periods differing from the compounding periods, we've actually looked at that. It's a different set of steps, but still need the number of compounding periods, the number of payments, the number of interest periods per payment, and it's still a straightforward calculation. You can do it now. In this case, you've got both discrete compounding or continuous compounding. If you have a situation of continuous compounding, and the total number of payments, and then you use the appropriate equivalence formula as before. Okay, again, give you a situation where I'm going to give you the numbers as we work through it pretty fast. Quarterly deposits with monthly compounding. Okay, if you compound monthly and you put quarterly deposits in, it's nice because those deposits that occur at, let's say, the beginning of a compound of quarterly periods would actually get that compounding over the period of time. But this is a plug and chug. Okay, step 1, 2, 3, 4. Okay, so for this specific one, we had quarterly deposits of I see in this case we did quarterly deposits of 1,000. This is the amount of money you would have at that percentage, at that interest rates at the end, future value. Continuous compounding, okay, slightly different equation and just in step 2. Okay, step 2 with the monthly compounding was 3.03 for that interest rate on that period. With continuous compounding, it comes out to 3.045, slightly larger. Okay, which in turn means that you would have more money at the end. Okay, C being infinity, but you have a different equation for that one, the continuous compounding equation. Okay, so a few of these, a series of equal quarterly payments of $5,000 for 10 years is equivalent to what present amount at an interest rate at 9%. And we can do this, actually, I'm going to do this on multiples when we're talking about compounded quarterly, monthly, and continuously, because you want to do the comparison of the different values. Okay, in the case of this one, in the case of quarters, you're talking about 40 quarters. You're talking about the interest rate per quarter. You can calculate that pretty straightly because you've got 40 quarters in those 10 years. P, okay, equals, okay, you've got that future value, and then you come back and get that specific period of time. Annual payment, present value. Monthly, calculating the present value again, but you have to do the application because you have the period, not, basically you have in this case a monthly versus in the payment period or quarterly, but the interest period being monthly. You just apply that first equation slightly differently. 40 quarters. I'm going to go backwards for one to do the comparison of the values. 130,968. Okay, 130,586. Okay, and continuously 133,884, slightly lower. Okay, now again, I'm going to put that in here so that you can look at those numbers, apply it to the equation, work through it, and make it make sense. Okay, the reality is that I'm going to go backwards just a little bit to those equations. Case 2, payment periods differing from compounding periods. You have the process. It's relatively straightforward, but really what you're doing is you're looking at getting an effective interest rate over a period, total number of payment periods, and then use the equivalence formula to get the actual value at any point in time. What we're doing is we're simply applying our equations in slightly different ways. Okay, I'm going to have you work a few examples because this makes a lot more sense when you start working through examples. Okay, that's it. I hope I didn't lose anybody on this one. Good time.